Welcome to our presentation on composites and jet engines, presented by me, Gabe, Owen, and Nupur. Composites in aerospace. The aerospace industry was an early adopter of composite materials. The industry alone utilizes over 20 million pounds of composites each year. These composites are largely used in military and commercial industries to reduce the weights of aircrafts. Applications can be seen in military aircrafts like the F-14, the F-15, F-16, B-1, and AV-8B. The commercial aircrafts applications can be seen in the Boeing 737, 757, and 767. Carbon epoxy laminates are a good example of a composite used in this industry, as they can give the benefit of a thermal expansion coefficient of 0. Additionally, composites can specifically be applied in the production of engine components such as the nose cone, vanes, fuel pumps, and inlet housings, to name a few. So the performance requirements for aerospace parts include reducing the weight, improving the thermal and dimensional stability. So lower weights in these parts can reduce the lift necessary, so engines can be more fuel efficient and produce less emissions. Parts are also expected to withstand high temperature and pressure fluctuations, so high thermal stability is necessary. Additionally, high dimensional stability is necessary due to the conditions parts have to withstand. Improvements here can improve the reliability and safety of aircrafts. The advantages of composites include making production easier, making it behave more consistently, and improving the strength to weight ratio. Parts manufactured for aerospace applications can often be complex and difficult to machine when working with metals, but manufacturing techniques available to the production of composites can make this much easier. Additionally, composites can be created to have a higher stiffness, which will produce way more consistent behavior in these parts, which is crucial in this industry. Finally, the improved strength to weight ratio gives aircrafts a much better fuel efficiency and reduced emissions. On the other hand, however, composites can be more expensive and sometimes not perform as well as metals. Composites are generally more labor intensive, uh, and for high performance parts, they can significantly increase the cost of manufacturing. Additionally, composites are unlikely to possess the same strength and temperature resistance that metals typically offer.
Ceramic matrix composites, often called CMCs, appear poised to be the next big development in jet engine materials. These materials are already in use in modern military engines, most notably in the exhaust nozzles of the F-135 on the F-35 Lightning II. Major manufacturers GE, Rolls-Royce, and Pratt & Whitney have all invested in research and manufacturing of these materials. CMCs provide great benefits and heat resistance relative to metal alloys, as well as weight, coming in at a third of the weight of most metals for the same part. Without the need for air cooling paths within the engine and reduced rotating mass, as seen with GE's prototype CMC blades in the second image here, much more freedom is granted for aerodynamics and design to improve efficiency. Furthermore, these parts need less investment in tooling to lay up, helping maintain costs compared to alloy counterparts. New designs for composite aircraft engines are always in the works, and a few concepts that heavily leverage composites are discussed here. Rolls-Royce's UltraFan is a new generation of wide-body engine from the supplier. It will be their first to utilize composite fan blades, and it uses the greatly reduced mast, 370 kilograms per engine, and moment of inertia of these spinning blades to create the largest fan of any jet engine in the world. 140 inches in diameter is 6 inches larger than the GE 9X, which is GE's current largest engine in production. Furthermore, as discussed previously, it uses extensive CMCs in its core to improve efficiency. Another new design concept comes from GE and Safran with their open fan engine. GE was the first to develop composite fan blades for a jet engine when it initially explored this concept in 1985, and it's seeking to bring back the design for modern materials to improve the efficiency as seen in initial testing. A 20% improvement in efficiency was seen with the original design, and GE aims to improve on this in its second iteration. As pictured here, this adds stators and a new rotor design to the already fleshed out open fan system that they've been looking at, all of which will be composite materials. The market for composite engines has been rapidly growing in the past few years, with nearly every new engine on the market featuring some use of composites throughout the design, and many making large composite components like fan blades a feature. This is because of the way the airline industry operates. Fuel costs are huge for carriers, and bringing down those fuel costs with lighter and more efficient engines is nearly always worth the added cost in procurement and maintenance. Fuel is always getting more expensive, so airlines will continue to seek these ever more efficient engines. This is the seen in the order numbers for the year, as every plane offered, sold, and delivered by current aircraft builders is powered by engines that heavily utilize composites in their designs. Looking at the list of orders for 2022 shown here, most common aircrafts we see are 737 and A320. Both Neo variants use composite fan blades, as well as extensive composites in their casings and the engines that power those aircraft. So composite engines are really dominating the middle of the market with those two mid-size single-aisle planes. Same with the A220 uses composite blades and composite casings, as well as the 787 and A350 are pretty well known for their composites use in the industry. Such prevalent use in industry demonstrates the utility of these materials that these materials provide their customers, and this utility will continue to grow with greater composites development.
For raw materials, carbon fiber epoxy composites are by far the most commonly used engine composites because of their prevalence in nacelles, which benefit from the high strength and stiffness of carbon fiber. Fiberglass can be used as a low-cost option in parts with lower strength requirements, though this isn't as common in engines as in the rest of the aircraft because there are fewer non-structural parts. And in general, the high performance is valued over low cost, which makes carbon fiber preferable to fiberglass. Aircraft exhaust is very hot and corrosive, so phenolic resins can be used in exhaust nozzles and other parts exposed to exhaust because they have good corrosion resistance and can't really burn. Thermoplastics often have worse properties than thermosets, but are used because they provide lower density and faster manufacturing times than thermoset resins. And finally, we have ceramic matrix composites. Currently, the most common are carbon-carbon-based CMCs. And these are a lot more difficult to manufacture than polymeric composites, and as a result are very expensive, but they can provide high strength and temperature resistance beyond what is seen in more typical epoxy-based composites. Nacelles are typically made using sandwich composites with foam honeycomb cores. These cores are especially selected to help reduce the vibration and noise that the engines produce. These structures are manufactured using open mold techniques like the one pictured here, and contrary to the usual composite logic of minimizing parts, the full nacelle is broken into pieces for easier manufacturing, and more importantly for serviceability and easier integration with the other engine components. Nozzles for lower service temperatures are typically carbon fiber composites and can thus be made with filament winding, which is one of the easiest ways of making hollow circular structures, in that either pre-preg tape or a wetted bundle of fibers is wound around a mandrel and then cured. So for higher service temperatures, ceramic matrix composites are instead used and have completely different manufacturing processes. So CMC processes depend on the thickness of your part and the composition of your reinforcing ceramic, among other things. And two common processes are hot press sintering and chemical vapor infiltration. In hot press sintering, it's a good option for solid parts where the components of the composite can be solid state sintered, for example, alumina. However, this doesn't work with carbon. So in carbon-based CMCs, infiltration techniques are more often used, where the matrix is made and the second phase is introduced as a liquid or gas, and then which allows it to impregnate the matrix before being solidified. Composite blades are not super common yet because their high performance requirements are not compatible with typical resins, and alternative manufacturing techniques are not well developed yet. One option is carbon-carbon laser-assisted tape winding, which is a modification of filament winding that is suitable to manufacture the more complex shapes seen in blades. And then again, you can use ceramic matrix composites.